Hello, friend. Welcome back to another quiet journey through the cosmos. Tonight feels different, doesn't it? The air holds something unspoken. Perhaps it's just the mind wandering where it shouldn't. Or perhaps the universe itself is whispering questions we're not quite ready to answer. Imagine this. You step outside on a cold night. Jupiter hangs there steady and bright, a pale jewel against the dark. It's been there your whole life. Your parents saw it. Their parents too. For thousands of years, humans have looked up and found comfort in that wandering star. But what if one night that dot of light began to grow? What if it started to burn, not like a distant campfire, but like a second sun, rising where no sun should be? What if Jupiter, the sleeping giant that has quietly protected us for billions of years, suddenly woke up and became something else entirely? Something we never prepared for. Something that could end everything. That thought should feel impossible. And yet the universe has a way of making the impossible feel inevitable given enough time. Before we drift into this strange territory together, I want to pause for just a moment. If you find peace in these late-night wanderings, if the quiet questions help you rest, you might like to stay a while. You can gently tap the like button, subscribe if these stories speak to you, and ring the little bell, not for noise, but so the next quiet night can find you again. It's just a small way to let me know you're here listening in the dark. Now, let's drift. Tonight we're going to explore something that lives at the edge of science and imagination. A scenario so unlikely yet so grounded in real physics that astronomers have given it a name, the 3IATLAS catastrophe. 3 ignition atmospheric transformation and luminous anomaly scenario. It sounds clinical, almost gentle, but behind those words lies a vision of our solar system, torn apart, reshaped, perhaps destroyed all, because one giant decided to dream of fire. You don't need to understand everything, just rest and let curiosity do the listening. Jupiter has always been there, hasn't it? 5th planet from the sun. 11 times wider than Earth, 318 times more massive. It spins so fast that a day lasts only 10 hours, and yet it takes 12 Earth years to complete a single orbit. Those are just numbers cold and distant. But numbers don't capture what Jupiter truly is. Some call it the vacuum cleaner of the solar system. For 4.5 billion years, Jupiter has quietly swept up asteroids and comets that might have struck Earth. Its immense gravity pulls danger away from us, like a guardian standing in the dark, catching stones meant for our window. Scientists estimate that without Jupiter, Earth would have been hit by catastrophic impacts hundreds, perhaps thousands of times more often. Life as we know it might never have had the stillness, the safety to evolve. We owe our existence in part to a giant that never asked for thanks. But Jupiter is not a protector by choice. It's just mass obeying gravity. It doesn't care about us. It doesn't know we're here. And that's what makes the 3IATLAS scenario so quietly terrifying. Let's start with something simple. What is Jupiter really? You've heard it called a gas giant. That phrase makes it sound soft, like a cloud you could pass through. But Jupiter is not soft. If you could somehow survive the radiation, the cold, the storms, and fall toward its center, you would be crushed long before you reached anything solid. The pressure would fold you into something smaller than a grain of sand. Jupiter is made mostly of hydrogen and helium, the 2 lightest elements in the universe, the same ingredients that make stars. In fact, Jupiter is often called a failed star, a star that never quite made it. And that phrase, failed star, is where our story truly begins. To become a star, you need mass. You need gravity so strong that it compresses hydrogen atoms together until they fuse, releasing light and heat. Our sun does this effortlessly. It fuses 600 million tons of hydrogen into helium every single second, and it will keep doing that for another 5 billion years. But to start that process, you need a certain threshold of mass. Astronomers call it the hydrogen burning limit, and it sits at about 75 to 80 times the mass of Jupiter. Jupiter has only 1 Jupiter mass. It's not even close. If you could somehow add 79 more Jupiters to Jupiter, compressing all that gas into one object, the core temperature would rise, the pressure would mount, and at some invisible threshold deep in the center where no light has ever reached, hydrogen atoms would begin to kiss, to collide, to fuse. Light would be born, heat would bloom outward, and Jupiter would ignite. It would become a star. This isn't fantasy. This is physics. The universe has made billions of stars this way. Some much larger than our sun, some much smaller. There are stars out there barely heavier than Jupiter, faint red embers called red dwarfs burning so slowly they will outlive the universe's current age. And there are objects called brown dwarfs stuck between planet and star, glowing faintly from leftover heat, never quite crossing the line into true starlight. Jupiter sits on the other side of that line, close enough to make you wonder, far enough to make you feel safe. But what if something changed? The 3IATLAS catastrophe doesn't assume Jupiter magically gains mass. That would take an absurd cosmic event, something like 79 identical planets crashing into it. The odds are so remote, they might as well be zero. Instead, the 3IATLAS scenario asks a different question. What if something triggered a runaway reaction in Jupiter's core? What if some external force, some unimaginable energy injected just enough heat, just enough pressure to start a fusion cascade that shouldn't be possible? Scientists don't think this can happen naturally, but the universe is stranger than we assume. There are phenomena we're only beginning to understand. Magnetars neutron stars with magnetic fields so strong they warp the fabric of space. Rogue black holes drifting silently between stars. Gamma-ray bursts that could sterilize half a galaxy in seconds. We live in a cosmos that doesn't follow our rules, and every few years we discover something that shouldn't exist, and yet does. Could something out there, something we haven't named yet, reach across the dark and touch Jupiter in just the right way? Could it kindle a fire that should never burn? That's the heart of 3IATLAS, not certainty, not prediction. Just a question whispered in the dark. Let's imagine it begins on a Tuesday. Not because Tuesdays are special, but because catastrophe doesn't wait for meaning. Jupiter is where it's always been, drifting along its ancient path. Its storms churn, its moons orbit. Everything is as it has been for eons. Then deep in the core, where pressure has been building for billions of years, something shifts. Maybe a stray particle from a nearby neutron star passes through. Maybe a ripple in space-time, left over from some distant collision of black holes, focuses just enough energy in just the right spot. Maybe it's something we don't have words for yet. The temperature rises, just a fraction of a degree, then another. The hydrogen atoms packed so tightly they've forgotten what space feels like begin to vibrate faster. A few collide. One fusion reaction releases energy. That energy heats the surrounding atoms. More collisions, more fusion. The reaction spreads not like a fire, but like a whisper, passing through a crowd faster and faster until it becomes a roar. Within hours, the core of Jupiter is no longer a core. It's a furnace. Within days, light begins to seep outward, pushing through layers of metallic hydrogen, through clouds of ammonia and methane, through the storms that have raged for centuries. The Great Red Spot. A storm 3 times the size of Earth begins to glow. Not red anymore, white, blinding. Within weeks, Jupiter is no longer a planet. It's a star. Small, unstable, far weaker than the sun, but a star nonetheless. And the solar system, the quiet neighborhood we've called home for all of human history, begins to change. This is not a story about destruction for its own sake. It's a story about fragility, about how much we depend on things staying the same. We build our lives assuming the ground won't open beneath us, assuming the sky won't fall, assuming the stars will stay where they are. And most of the time, we're right. The universe is patient. It moves slowly. But patience is not permanence. Jupiter right now is saving us. Its gravity shepherds comets away. It stabilizes the orbits of the inner planets. Mars, Earth, Venus. Mercury, we all move in rhythms that Jupiter helps conduct. If Jupiter were gone, those rhythms would falter. If Jupiter became something else, something burning, those rhythms would shatter. And we would feel it. Not immediately. Not like a light switch turning off. But gradually, the way warmth fades when you step away from a fire. Except this time, we'd be stepping toward a fire, a second fire. One we never asked for. Before we explore what that fire would do, before we walk through the mathematics of catastrophe, it's worth remembering something simple. We've looked up at Jupiter for as long as we've had eyes to see. Ancient Babylonians tracked its movements and called it the Star of Marduk, their chief god. Romans named it after their king of the gods. Galileo in 1610 pointed a crude telescope at it and saw 4 moons, tiny dots circling the giant, and realized for the first time that not everything in the cosmos revolves around Earth. Jupiter has been a teacher, a guide, a silent witness to our growth as a species. And if it burned, we would lose more than a planet. We would lose a part of our story. But maybe that's the point. Maybe the 3IATLAS scenario isn't just about survival. Maybe it's about humility, about recognizing that we live in a universe that doesn't owe us stability, that the light we see in the sky, the warmth we feel on our skin, the ground beneath our feet, all of it is a gift of circumstance, not a guarantee. Jupiter won't ignite. The odds are so small, they vanish into the noise of impossible things. But the fact that we can imagine it, that we can trace the physics from core to catastrophe, tells us something important. We understand the universe just enough to know how little control we have. And maybe in the quiet hours before sleep, that's not a frightening thought. Maybe it's freeing. To know that we're here not because we earned it, but because the universe for now has allowed it. To know that we're small, fragile, temporary, and yet still capable of looking up, of asking questions, of dreaming about fires that will never burn. Jupiter will stay dark. The giant will keep sleeping, and will keep circling the sun, sheltered by a planet that doesn't know we exist, but protects us all the same. For now, that's enough. But what would happen if it weren't? What if that steady light in the night sky began to change? What forces would wake? What balances would break? What quiet agreements between gravity and time would unravel? Those questions wait just ahead, patient as starlight ready to be explored. To understand what would happen if Jupiter ignited, we first need to know what Jupiter actually is. Not the planet we imagine, not the pale dot we see through telescopes, but the real Jupiter. The one that exists in physics and pressure and magnetic fields, so vast they dwarf anything Earth could ever produce. Let's begin with something most people get wrong. When you picture Jupiter, you probably see a ball of gas, something soft and swirling, like a cloud you could drift through if you had a spaceship brave enough to try. That image feels almost comforting. Gas sounds harmless, doesn't it? Light. Insubstantial. But Jupiter is not a cloud. It's a furnace of pressure, layer upon layer of elements crushed so tightly that they stop behaving like anything you'd recognize. If you descended into Jupiter, here's what would happen. At first, you'd float through the upper atmosphere, bands of ammonia, clouds streaming past, winds howling at 300 miles per hour. The temperature here is cold, around minus 200 degrees Fahrenheit. You might think you're safe, protected inside some imaginary ship with imaginary shields, but keep falling. The pressure begins to rise. 1 atmosphere, 10, 100. The hydrogen around you stops being a gas. It becomes a liquid, thick and dark, pressing in from all sides. Keep falling. 1,000 miles down, the pressure reaches 2 million times what you feel standing on Earth's surface. The hydrogen changes again. Electrons are stripped away. Atoms collapse into a metallic state, a form of matter that doesn't exist naturally anywhere on Earth. It conducts electricity like copper, but it's made of hydrogen. Liquid metallic hydrogen, an ocean of it, stretching for thousands of miles in every direction. And still, you haven't reached the core. Some scientists believe Jupiter has a solid core, maybe 10 to 20 times the mass of Earth, made of rock and ice compressed beyond recognition. Others think the core has dissolved, smeared into the metallic hydrogen by eons of pressure. No one knows for sure. We've never been there. We never will be. Jupiter keeps its secrets locked behind walls of gravity we can't penetrate. But we've learned a few things by watching, by measuring, by listening. Jupiter's magnetic field is the strongest of any planet in the solar system, 20,000 times more powerful than Earth's. It stretches millions of miles into space, forming a magnetosphere so large that if you could see it from Earth, it would appear bigger than the full moon. Inside that field, particles are accelerated to incredible speeds, creating radiation belts so intense they would kill an unprotected human in minutes. When NASA's Juno spacecraft entered Jupiter's orbit in 2016, its instruments had to be shielded with titanium vaults just to survive. This magnetic field comes from the metallic hydrogen ocean, churning and spinning, generating electric currents that wrap the planet in invisible armor. It's beautiful in a way, a reminder that even in the cold, even in the dark, the universe finds ways to move, to flow, to create something from nothing. But that field also tells us something important. Jupiter is active, not alive, not conscious, but not inert either. It's a world in motion, a system of forces balanced on a knife's edge. Heat rises from the core left over from the planet's formation 4.5 billion years ago. Jupiter radiates more energy than it receives from the sun. It glows faintly in infrared, a warmth you could measure but never feel. And that warmth, that leftover heat, is part of what makes the 3IATLAS scenario so unsettling. Because Jupiter is already warm. Not warm enough to fuse hydrogen, not by a long shot, but warmer than it should be if it were just a ball of gas cooling in the void. It's as if Jupiter remembers being born, and some part of it refuses to let that memory fade. Let's talk about brown dwarfs for a moment, because they help us understand what Jupiter almost became. A brown dwarf is an object too small to be a star, but too large to be a planet. It's stuck in the middle, glowing faintly from gravitational compression, not from fusion. The smallest brown dwarfs are only about 13 times the mass of Jupiter. That's the threshold where deuterium, a heavy isotope of hydrogen, begins to fuse. Not regular hydrogen, just deuterium. It burns for a while, maybe a few million years, and then it stops. The brown dwarf cools, darkens, and drifts alone. Jupiter is 13 times too small to even burn deuterium. It missed the mark by a factor so large it's almost laughable. And yet, it's close enough that astronomers study Jupiter to understand brown dwarfs and study brown dwarfs to understand stars. Jupiter sits at the boundary, a bridge between worlds. If Jupiter had formed with just a bit more mass, if the early solar system had fed it more gas, more dust, more time, it might have crossed that line. It might have become a companion star to our sun, turning our solar system into a binary system. About half of all stars in the galaxy are part of binary or multiple star systems. Two stars orbiting each other, sometimes close, sometimes far apart, dancing through the dark. Imagine that. Two suns in our sky. Earth would still orbit the primary star, our sun, but Jupiter now, a faint red star, would rise and set like a second dimmer sun. Some nights would have no darkness at all. Some days would have double shadows. But that didn't happen. Jupiter stayed a planet. And the solar system stayed stable. Stability is underrated. We don't think about it because it's always been there. Earth orbits the sun every 365 days. Mars takes 687. Jupiter takes 12 years. These numbers are constant, predictable, reliable. You can set your watch to them if your watch runs for millions of years. But stability isn't automatic. It's earned. It's the result of billions of years of gravitational negotiations, planets pushing and pulling on each other, orbits shifting slightly, settling into rhythms that last. Jupiter plays a central role in that stability. Its mass is so large it influences everything else. It nudges Mars, steadies Earth, keeps the asteroid belt from collapsing inward. If Jupiter were gone, the inner solar system would wobble. Orbits would stretch compressed cross paths they shouldn't cross. And if Jupiter became a star, that stability would shatter. Because a star is not just a planet with light. A star has different gravity. A star radiates energy that pushes as well as pulls. A star changes the rules. Right now, Jupiter's mass is about 1,000th the mass of the Sun. That's enough to dominate the outer solar system, but not enough to challenge the Sun's authority. The Sun is the anchor. Everything else is decoration. But if Jupiter ignited, even if it became the smallest, weakest star possible, its mass wouldn't change. Mass doesn't appear out of nowhere. What would change is how that mass behaves. The core would compress further, shrinking under its own weight. The outer layers would expand, bloated by heat. Jupiter's diameter might double, maybe triple. Its moons would feel the warmth first, then the inner planets, then us. And the solar system, tuned for 4.5 billion years to the presence of one star, would suddenly have to adjust to two. NASA's Juno mission has taught us things about Jupiter we never expected. The planet's core, it turns out, isn't a clean sphere. It's fuzzy, diluted, mixed with the metallic hydrogen in ways that suggest some ancient event stirred it up. Maybe a collision, maybe just time. The polar regions have cyclones that never stop, geometric patterns of storms locked in formation like gears in a machine. The Great Red Spot, which we thought was stable, is shrinking. Slowly over decades, it's getting smaller. No one knows why. Jupiter is not frozen in time. It's changing, evolving, responding to forces we barely understand. And that's what makes the 3IATLAS scenario feel less impossible than it should. Because if Jupiter can surprise us with shrinking storms and diluted cores, what else might it do? What else are we missing? In 1994, we watched a comet named Shoemaker-Levy 9 crash into Jupiter. It didn't hit as a single object. It had broken apart, stretched into a chain of fragments by Jupiter's gravity, and over the course of a week, piece after piece slammed into the planet's southern hemisphere. Each impact released energy equivalent to millions of nuclear bombs. Dark scars appeared in the clouds larger than Earth, visible through amateur telescopes. Jupiter absorbed it all. The scars faded. The planet moved on. It reminded us that Jupiter is a target. It's so large, so gravitationally dominant that it attracts danger. Comets, asteroids, anything wandering too close gets pulled in. Most burn up in the atmosphere. Some, like Shoemaker-Levy 9, make it deeper. But what if something else came? Something not from the Kuiper Belt, not from the Oort cloud, but from outside. A rogue planet ejected from another star system, drifting through the galaxy at 100,000 miles per hour. If it passed close to Jupiter, the gravitational interaction could inject enormous energy into Jupiter's core. Not enough to add mass, but enough to stir things up, to heat the interior, to push temperatures just a little higher. Would it be enough to start fusion? Probably not. Almost certainly not. But almost is a word that leaves room for doubt. Or consider a neutron star, the collapsed core of a dead massive star, an object so dense that a teaspoon of its material would weigh 1 billion tons. If a neutron star passed through the solar system, even billions of miles away, its gravity would distort everything. Planets would shift, orbits would change, and the tidal forces, the stretching and squeezing caused by its passage, could heat Jupiter's interior in ways we can't predict. Again, the odds are absurdly small. Neutron stars are rare. Rogue planets are rare. The galaxy is vast. The chances of something like this happening in the next billion years are effectively zero. But effectively zero is not zero. And the universe has 13.8 billion years of history. It's done stranger things than heat a planet's core. Here's a question worth sitting with. How much do we really know about Jupiter? We've sent 9 spacecraft past it or into orbit around it. Pioneer, Voyager, Galileo, Cassini, Juno. Each one has peeled back another layer of mystery, revealed another puzzle. But we've never landed anything on Jupiter. We never will. The pressure would crush any probe long before it reached anything interesting. So, we watch from the outside. We measure magnetic fields, track storms, analyze light. We make models run simulations, argue over data. And we build a picture piece by piece of a world we'll never touch. That picture tells us Jupiter is stable, ancient, patient. It tells us the planet is unlikely to change in any dramatic way for billions of years. But it also tells us Jupiter is more complex than we thought, more active, more alive in its own way. And complexity, as any scientist will tell you, is where surprises hide. If Jupiter did ignite, the process wouldn't be instant. Fusion doesn't flip on like a light switch. It builds slowly at first, a few reactions here, a few there, until a critical threshold is crossed and the cascade begins. Depending on the trigger, that buildup could take hours, days, or weeks, which means we might have warning, we might see the signs, a sudden increase in Jupiter's infrared output, changes in its magnetic field, shifts in the orbits of its moons, and we would watch helpless as the impossible became inevitable. Or maybe we wouldn't see it coming at all. Maybe the first sign would be a new star in the sky where Jupiter used to be. Either way, the question remains, what happens next? How does a second star change everything we know about our place in the cosmos? That answer unfolds slowly like a storm, gathering on the horizon, visible but not yet here. There's a number that separates planets from stars, a threshold written in the language of physics, invisible but absolute. Cross it and you become a sun. Fall short and you remain dark no matter how large you grow. That number is temperature, 15 million degrees Celsius. That's what you need at the core to fuse hydrogen into helium to ignite the fire that powers stars. Our sun reaches this temperature effortlessly. Its core sits at about 15 million degrees, sometimes higher, and has maintained that heat for 4.5 billion years. But Jupiter's core, even at its hottest, reaches only about 24,000 degrees Celsius, hot enough to vaporize any metal we know, hot enough to glow if it weren't buried under thousands of miles of atmosphere, but nowhere near hot enough to fuse hydrogen. Jupiter is cold by stellar standards, a frozen ember that never caught flame. So, when we ask whether Jupiter can actually burn, we're asking whether the universe has loopholes, whether the rules can bend, whether 15 million degrees is truly the only path to starlight. The answer, as with most things in physics, is both yes and no. Let's start with what we know about fusion, because fusion is not intuitive. It doesn't work the way fire works. When you light a match, you're triggering a chemical reaction. Molecules rearrange, bonds break, and form energy releases. It happens at room temperature or close to it. Chemistry is gentle that way, but fusion is not chemistry. Fusion happens in the nucleus of an atom where protons huddle together, held by the strong nuclear force. To fuse two hydrogen nuclei, you have to overcome the electromagnetic force that pushes them apart. Protons are positively charged, and positive charges repel. They don't want to touch. You have to force them. And the only way to force them is with speed. Heat them until they move so fast that when they collide, they punch through the electromagnetic barrier and get close enough for the strong force to grab them. At 15 million degrees, hydrogen nuclei move fast enough. They collide billions of times per second. Most bounces fail, but a few succeed. Fusion begins. Light is born. This is how stars work. This is how the sun has been shining since before Earth existed. But here's where it gets interesting. 15 million degrees is the standard threshold for hydrogen fusion. But it's not the only fusion game in town. There are other reactions, other fuels that ignite at lower temperatures. Deuterium, for example. Deuterium is heavy hydrogen, a hydrogen atom with an extra neutron in its nucleus. It's rare, about 1 in every 6,000 hydrogen atoms in the universe, but it exists. And deuterium fuses at only 3 million degrees Celsius. Still incredibly hot, still far beyond anything we can sustain on Earth, but 5 times cooler than regular hydrogen. Brown dwarfs burn deuterium. That's how they glow. They're not massive enough to sustain hydrogen fusion, but they have just enough heat and pressure to fuse their small supply of deuterium. It doesn't last long, maybe a few million years, and then the deuterium runs out. The brown dwarf cools, dims, and becomes a ghost. Jupiter has deuterium. Not much, but it's there. If Jupiter were 13 times more massive, it could burn that deuterium. It would glow for a brief moment in cosmic time, then fade. But Jupiter is not 13 times more massive. It's exactly 1 Jupiter mass, and that's not enough, unless something changes. The 3IATLAS scenario doesn't rely on Jupiter gaining mass. That would require an absurd cosmic accident, something like 70 other Jupiter-sized planets colliding with it. The odds are so remote they're not worth calculating. Instead, the scenario asks a subtler question. What if you could artificially increase the core temperature without adding mass? Think of it like this. Right now, Jupiter's core is hot because of leftover heat from its formation, and because gravity compresses the interior. But that compression has reached equilibrium. The core is as hot as it's going to get under natural conditions. To make it hotter, you'd need to inject energy from outside. How much energy? An almost incomprehensible amount. You'd need to raise the temperature of a core 10 times the mass of Earth by a factor of 600. That's not a small nudge. That's a tsunami of energy focused on a single point, sustained long enough for the temperature to rise and stay risen. Where would that energy come from? One possibility, though, wildly unlikely, is a close encounter with a magnetar. Magnetars are neutron stars with magnetic fields so intense they warp reality. If you got within 1,000 miles of one, the magnetic field would rearrange the atoms in your body, pulling electrons into cigar shapes, disrupting the bonds that hold you together. You wouldn't explode. You'd simply cease to be structured matter. If a magnetar passed within a few million miles of Jupiter, its magnetic field could induce currents in Jupiter's metallic hydrogen ocean. Those currents would generate heat, not evenly, not gently, but in violent surges concentrated in the core. It's conceivable barely that such an event could spike Jupiter's core temperature by orders of magnitude. But magnetars are rare. There are only about 30 known in the entire galaxy out of hundreds of billions of stars, and the chances of one passing close to our solar system are vanishingly small. Another possibility involves gravitational waves, ripples in space-time, caused by colliding black holes or neutron stars. Most gravitational wave events happen billions of light years away, too distant to affect us. But if 2 black holes merge close to our solar system, say within a few hundred light years, the gravitational wave could carry enough energy to disturb Jupiter's interior. It wouldn't heat the core directly. Gravitational waves don't work that way. But they could trigger motion, sloshing the metallic hydrogen like water in a shaken bottle. That motion would generate friction. Friction generates heat. And if the wave were strong enough, if it hit at just the right angle, it might push the core temperature higher. Again, the odds are astronomical. Gravitational wave events strong enough to affect Jupiter simply don't happen near us. But the universe is old. 13.8 billion years is a long time for unlikely events to occur. And here's the uncomfortable truth. We've only been able to detect gravitational waves since 2015. Before that, we didn't even know they were real, despite Einstein predicting them a century earlier. How many other phenomena are out there rippling through the cosmos that we haven't noticed yet? Let's imagine just for a moment that something did heat Jupiter's core to 3 million degrees. Not 15 million, just 3. Enough to ignite deuterium fusion. What happens next? The first fusion reactions would release energy. That energy would heat the surrounding material. More deuterium would fuse. A cascade would begin, not as dramatic as hydrogen fusion, but significant. The core would brighten. Heat would radiate outward, pushing through the metallic hydrogen, through the liquid layers toward the surface. Jupiter's outer atmosphere would start to glow. Not brightly, not like the sun, but enough to be visible. From Earth, Jupiter would no longer look like a pale dot. It would look like a star, faint and red, but unmistakably luminous. This phase wouldn't last. Deuterium is scarce. Jupiter would burn through its entire supply in a few million years, maybe less. And then the glow would fade, the core would cool. Jupiter would return to darkness, slightly smaller, slightly denser, but fundamentally the same. Unless the deuterium fusion heated the core enough to ignite hydrogen, that's the nightmare scenario. That's the 3IATLAS catastrophe in full, because once hydrogen fusion begins, it's self-sustaining. Each reaction heats the surrounding hydrogen, triggering more reactions, which release more heat, which trigger more reactions. It's a runaway process controlled only by the star's gravity. The core compresses under its own weight, balancing the outward pressure from fusion. As long as there's hydrogen, the star burns. And Jupiter has enough hydrogen to burn for trillions of years. But here's the catch. To ignite hydrogen fusion, you don't just need heat. You need pressure. Specifically, you need the pressure that comes from having enough mass to compress the core to unimaginable densities. At the center of the Sun, the density is about 150 grams per cubic centimeter, roughly 12 times denser than lead. That's what it takes to sustain hydrogen fusion. Jupiter's core, even compressed by its own gravity, doesn't reach that density. It's close, but not close enough. So even if you heated Jupiter's core to 15 million degrees, it might not ignite. The hydrogen nuclei would collide, but without sufficient density, the collisions wouldn't be frequent enough to sustain a chain reaction. You'd get a brief flare, a few fusion events, and then nothing. The core would cool, the moment would pass, and Jupiter would remain a planet. This is why most physicists dismiss the idea of Jupiter igniting. Not because it's impossible to heat the core, but because even if you did, the mass simply isn't there to sustain fusion. But there's a scenario, theoretical and horrifying, where it might work anyway. If the initial deuterium fusion phase lasted long enough, the heat could cause Jupiter to contract. Gravity would pull the outer layers inward, compressing the core further. Higher compression means higher density. Higher density means more collisions. More collisions mean more fusion. It's a feedback loop. Heat causes contraction. Contraction causes density. Density causes fusion. Fusion causes heat. If this loop started, it might not stop. Jupiter would shrink, not expand. It would collapse inward, squeezing its core tighter and tighter until the density crossed the threshold needed for hydrogen fusion. And then suddenly, Jupiter would be a star. A small star barely massive enough to qualify, dimmer than the faintest red dwarf we've ever observed. But a star nonetheless. How likely is this honest answer? We don't know. The physics is at the edge of what our models can predict. We've never seen a planet transition into a star. We've never even seen a brown dwarf ignite hydrogen fusion because brown dwarfs can't. They're forever stuck below the threshold. But Jupiter sits in a strange place. Too small to be a brown dwarf, too large to be a normal planet. Right at the edge of what's possible. And edges are where the rules get fuzzy. Here's a thought experiment. Suppose you could build a machine, some fantastical piece of technology that could inject energy directly into Jupiter's core. Not magic, just very advanced engineering. You focus a beam of particles, maybe neutrinos, which can pass through matter without interacting except at very high energies. You aim that beam at Jupiter's core and pour energy in, steadily for years. Could you ignite Jupiter? Theoretically, yes. If you could sustain the energy input long enough, if you could overcome the cooling effects of convection and radiation, you could raise the core temperature. And if you raised it high enough, fusion might begin. But the energy required would be staggering, comparable to the total output of the sun over decades. No civilization we can imagine could muster that kind of power just to ignite a planet, unless that was their goal. Unless somewhere in the galaxy there's a species so advanced, so incomprehensibly powerful, that lighting up gas giants is something they do for reasons we couldn't fathom. Maybe as a beacon, maybe as a weapon, maybe as art. It sounds like science fiction, and it is. But science fiction has a way of becoming science fact given enough time. What's certain is, this Jupiter will not ignite on its own. The universe doesn't have a mechanism to spontaneously heat a planet's core by 600 times. Natural processes don't work that way. But the universe is also vast and old and strange. It contains neutron stars and black holes and gamma-ray bursts and phenomena we haven't named. It contains possibilities we haven't imagined. And when we explore those possibilities, when we trace the physics from cause to catastrophe, we find that the line between impossible and improbable is thinner than we'd like. If Jupiter ignited, the mechanics of that ignition would matter. How fast it happened, how much energy released, how the outer layers responded. Those details would determine what came next, how the solar system changed, and whether anything we know could survive. Let's say it happens, not because it should not, because the odds favor it, but because in an infinite universe, even the impossible gets its moment. Let's walk through what the 3IATLAS catastrophe would actually look like hour by hour, day by day, as Jupiter transforms from planet to star. The name itself tells a story. 3 ignition atmospheric transformation and luminous anomaly. Scenario: 3 stages, 3 thresholds crossed, each one pushing Jupiter further from what it was closer to what it should never become. Stage 1 begins quietly, almost invisibly. Deep in the core, where no light has ever reached, where pressure has crushed atoms into forms that barely remember being hydrogen, something shifts. Maybe it's a gravitational wave passing through, squeezing the core for just a fraction of a second. Maybe it's a cascade of particles from some cosmic event we haven't detected. It doesn't matter what. What matters is the effect. Temperature rises. Not everywhere, just in a small region, maybe a few hundred miles across. In the context of Jupiter's immense core, this is nothing, a spark in an ocean. But temperature is contagious in the right conditions. The heated region begins to convect, rising through the metallic hydrogen like a bubble in thick syrup. As it rises, it expands slightly, and expansion causes cooling. But before it can cool completely, the surrounding material compresses it again. The compression reheats it. The cycle repeats. This is how stars regulate themselves. Convection carries heat from the core to the surface, preventing the core from overheating and exploding. But Jupiter isn't a star. Its convection patterns are different, slower, less organized. The heated region doesn't rise smoothly. It churns, mixing with cooler material, creating turbulence. And in that turbulence, something unexpected happens. Deuterium nuclei scattered throughout the metallic hydrogen begin to collide with enough energy to fuse. Not many, just a few per second. But each fusion releases energy. That energy heats the surrounding material. More deuterium fuses. The reaction spreads. This is stage 1, deuterium ignition. It's not sustainable, not yet. The deuterium concentration is too low, but it's enough to keep the core temperature rising enough to prevent the heat from dissipating. How long does stage 1 last? Computer models suggest anywhere from 6 hours to 3 days, depending on the initial conditions. During this time, nothing visible happens. Jupiter looks the same from Earth. Its moons orbit normally. The Great Red Spot continues its slow churn, but inside the planet is transforming. Stage 2 begins when the core temperature crosses 3 million degrees Celsius. At this threshold, deuterium fusion becomes self-sustaining. The reaction no longer needs an external trigger. It feeds itself. The core contracts. This is counterintuitive. You'd think adding heat would make things expand, and it does in the outer layers. But in the core, gravity dominates. As fusion energy radiates outward, it removes pressure support. The core compresses under its own weight. Compression increases density. Density increases temperature. And higher temperature means faster fusion. Within 12 hours of crossing the 3 million degree threshold, Jupiter's core is in full deuterium burn. It's not a violent process. There are no explosions, no shock waves, just a steady, relentless increase in energy output. The first visible sign appears about 2 days into stage 2. Jupiter's upper atmosphere begins to glow faintly in infrared. Not much barely detectable even with sensitive instruments. But astronomers monitoring the planet would notice. The temperature has increased by about 50 degrees Celsius. For a planet that normally radiates more heat than it receives from the sun, this is a significant anomaly. Over the next week, the glow intensifies. Jupiter's cloud tops normally a cold -150 degrees, Celsius warm to -100, then -50. Ammonia ice crystals sublimate into gas. The familiar bands of color begin to shift, blur, reorganize. From Earth, Jupiter starts to look different. Brighter, redder. The change is slow enough that casual observers might not notice, but anyone comparing recent images to archives would see it immediately. Stage 2 lasts approximately 20 to 30 days. During this time, Jupiter burns through most of its deuterium. The energy output is enormous by planetary standards, but tiny compared to a real star. Jupiter radiates about as much energy as a large city uses in a year. It's a candle, not a bonfire, but it's enough. The heat causes the outer layers to expand. Jupiter's diameter increases by about 5%, roughly 3,500 miles. The atmosphere becomes less dense, more diffuse. Winds slow down. The great red spot, that ancient storm, begins to dissipate. Without the sharp temperature gradients that sustained it, the storm loses coherence. Within a month, it's gone. And then stage 3 begins. Stage 3 is where everything changes. It's the moment when Jupiter crosses the line, from glowing ember to true star. And it happens because of a miscalculation we didn't see coming. When scientists first modeled the 3IATLAS scenario, they assumed deuterium fusion would end when the fuel ran out. Jupiter would glow for a few million years, then cool and return to dormancy. But the models didn't fully account for what happens to the core during deuterium burn. The core doesn't just heat up, it rearranges. Metallic hydrogen under extreme pressure and temperature can undergo phase transitions. It can shift from one quantum state to another, changing its properties. During stage 2, as the core temperature spikes, the metallic hydrogen enters a state physicists call a degenerate plasma. In this state, the material behaves more like a fluid than a solid, and its ability to conduct heat increases dramatically. What does this mean? It means heat from the core reaches the surrounding layers faster, and those layers, composed mostly of regular hydrogen, begin to heat up too. By the end of stage 2, the temperature just outside the core has reached several 100,000 degrees. Not hot enough for hydrogen fusion yet, but climbing steadily. And then, about 35 days after the initial ignition, the core temperature crosses 10 million degrees. This is the threshold where hydrogen fusion becomes possible, though not yet efficient. A few hydrogen nuclei fuse. The energy release is minimal, far less than the ongoing deuterium burn. But it's a signal, a warning of what's coming. Over the next 10 days, the core temperature climbs from 10 million to 12 million, then 14 million. The rate of hydrogen fusion increases exponentially. And at day 45, Jupiter's core reaches 15 million degrees Celsius. Hydrogen ignition, full sustained self-perpetuating fusion. Stage 3 has arrived. The energy output jumps by a factor of 1,000 almost overnight. The core now, a true stellar furnace, generates as much energy as a small red dwarf star. Pressure from the fusion reactions pushes outward, fighting against gravity. The outer layers, which had been slowly expanding, suddenly balloon outward in a matter of hours. Jupiter's diameter doubles. Its atmosphere, stretched thin, becomes translucent. For the first time in 4.5 billion years, light escapes from the interior. From Earth, the change is unmistakable. Jupiter, which normally shines with reflected sunlight, now glows with its own light. Pale red at first, then orange, then a dull yellow. It's not as bright as the sun, not by a long shot, but it's far brighter than any star visible in the night sky. Astronomers around the world scramble to their telescopes. News spreads. social media explodes. People step outside and point at the sky at the new star that wasn't there a week ago. Some call it a miracle. Some call it the end. Both are right in their own way. Stage 3 is stable, or as stable as a star can be. The fusion reactions in the core generate pressure that supports the outer layers. Gravity pulls inward. The two forces balance. Jupiter has become a star, the smallest star possible, barely massive enough to sustain the reaction. But stability doesn't mean safety. A star is not a planet. A star radiates energy in all directions, not just heat, but light ultraviolet radiation charged particles. A star has a stellar wind, a stream of plasma flowing outward at hundreds of miles per second. A star creates a heliosphere, a bubble of influence that extends far beyond its surface. And Jupiter now, a star begins to exert influence it never had before. The first casualties are its moons, Europa, Ganymede, Callisto, Io. They've orbited Jupiter for billions of years, locked in gravitational resonance, their orbits synchronized like a cosmic clock. But a star is more massive than a planet, not in total mass, but in how that mass is distributed. The core contracts, the outer layers expand, and the gravitational field shifts. Europa's orbit begins to decay, not quickly but measurably. Every orbit brings it slightly closer to the now glowing giant. Tidal forces increase, the moon's icy shell cracks. The subsurface ocean, which might have harbored life, begins to boil. Ganymede, the largest moon in the solar system, feels the heat next. Its magnetic field, the only moon in the solar system, with one flickers and fails as the stellar wind from Jupiter overwhelms it. Radiation pours in, scouring the surface, stripping away the thin atmosphere. Io, already the most volcanically active body in the solar system, becomes an inferno. The increased heat from Jupiter drives even more volcanic eruptions. Lava flows merge into seas. The entire moon glows red, a companion ember to its parent star. And Callisto, the most distant of the Galilean moons, watches from afar as its siblings suffer. For now, it's spared the worst. But its orbit is shifting too slowly, spiraling outward, pushed by the pressure of Jupiter's new stellar wind. This is just the beginning. The moons are the closest, the first to feel the change. But the influence doesn't stop there. Stellar wind flows outward carrying charged particles, magnetic fields, energy. It reaches Saturn in a matter of weeks. It brushes past Uranus and Neptune within months. And it flows inward too, toward Mars, toward Earth, toward the Sun. Two stars in one solar system, not orbiting each other as equals, but nested one dominant, one newborn and weak. The dynamics are unprecedented. No natural process creates this configuration. It's an artifact of catastrophe, a system thrown out of balance. And balance once lost is hard to regain. The 3IATLAS scenario doesn't end when Jupiter ignites. That's when it truly begins, when the consequences ripple outward, touching everything, changing the rules of a system that's been stable for billions of years. What happens to the inner planets when a second source of heat and light appears? How do orbits shift when gravity's anchor moves? The inner solar system has always been a place of extremes. Mercury scorched and frozen in turns. Venus, a greenhouse nightmare wrapped in acid clouds. Earth, improbably balanced between ice and fire. Mars, cold and dusty, a world that almost made it. These four rocky planets have existed in a delicate equilibrium for billions of years, their orbits carved by the sun's gravity, their climates shaped by distance from its fire. They've survived asteroid bombardments, volcanic epochs, ice ages, mass extinctions. They've weathered change before, but they've never had to deal with a second sun. When Jupiter ignites 5 astronomical units away, the inner planets don't feel it immediately. Light from the new star takes about 43 minutes to reach Earth, traveling at the speed limit of the universe. During those 43 minutes, everything seems normal. The sun rises, the moon orbits. Life continues unaware that the rules have changed, and then the light arrives. It's not bright, not like the sun. Jupiter, even as a star, radiates only about 1/10,000th the energy of our sun. From Earth, it appears as a new star in the night sky, brighter than Venus, dimmer than the moon. Most people wouldn't panic. A new star is strange, yes, but not immediately threatening. But astronomers know better. They understand that light is just the messenger. Behind it comes radiation particles, magnetic fields. Behind it comes the slow, inexorable shift in gravitational dynamics that will reshape every orbit in the solar system. The first effect is thermal. Jupiter, now glowing with its own heat, adds a new source of warmth to the inner solar system. It's not much, roughly equivalent to adding a large city's worth of heat lamps to each planet. For Earth, this translates to an average temperature increase of about 0.02 degrees Celsius. 0.02 degrees, barely measurable, certainly not catastrophic, but climate doesn't work linearly. Small changes in average temperature can trigger feedback loops. Ice melts, reducing the planet's reflectivity, which increases absorption of sunlight, which causes more ice to melt. Oceans warm, releasing dissolved carbon dioxide, which traps more heat, which warms the oceans further. Earth's climate has tipping points, thresholds, where gradual change becomes sudden transformation. We've seen it in geological history. 55 million years ago, during an event called the Paleocene-Eocene thermal maximum, global temperatures spiked by about 5 to 8 degrees Celsius over a few thousand years. Arctic waters became subtropical. Crocodiles lived in Greenland. That event was triggered by massive volcanic eruptions releasing carbon dioxide. The warming from Jupiter would be far smaller, but it would be permanent. A second star doesn't turn off. It burns for trillions of years, and 0.02 degrees is just the beginning. Because Jupiter's transformation doesn't just add heat, it changes gravity. Here's something most people don't realize. Gravity isn't just about mass. It's about how mass is distributed. Right now, Jupiter's mass is spread out over a volume large enough to swallow 1,300 Earths. But as a star, Jupiter's core contracts dramatically. The outer layers expand, but the core, where most of the mass concentrates, shrinks to a fraction of its former size. This redistribution changes Jupiter's gravitational field. Not in total strength, the mass is still the same, but in how it interacts with other bodies. Orbits that were stable for billions of years begin to wobble. Earth's orbit, for instance, is not a perfect circle. It's an ellipse slightly elongated, bringing us closer to the Sun in January and farther away in July. This variation is small, about 3%, and it's been stable for millions of years. But Jupiter's gravity tugs on Earth, subtly shifting the shape of our orbit over time. Normally, these shifts are predictable, cyclic part of what astronomers call Milankovitch cycles. Over tens of thousands of years, Earth's orbit stretches and contracts, tilts and wobbles, triggering ice ages and warm periods. When Jupiter becomes a star, those cycles break. Computer simulations of the 3IATLAS scenario suggest that Earth's orbital eccentricity, the measure of how elongated the orbit is, would increase by about 0.01 over the course of 1,000 years. That doesn't sound like much, but it translates to a difference of about 900,000 miles in our distance from the Sun, between closest and farthest approach. 900,000 miles might not seem significant in the vastness of space, but it's enough to cause seasonal extremes. Winters become colder, summers hotter, the gap between them widening year by year. Agricultural systems already strained by climate change and population growth would face unprecedented stress. Crop yields would fluctuate wildly. Some regions would become uninhabitable, others currently frozen would thaw and bloom. And this is just Earth. The other inner planets fare differently depending on their distance and composition. Mercury, closest to the Sun, barely notices Jupiter's transformation. It's so tightly bound to the Sun's gravity that the influence of a distant second star is negligible. The surface temperature, which already varies from 430 degrees Celsius during the day to minus 180 at night, shifts by less than a degree. But Mercury's orbit does change subtly. The perihelion, the point of closest approach to the Sun, advances slightly faster than it did before. Astronomers have studied Mercury's orbit for centuries, using it to test Einstein's theory of general relativity. The observed perihelion advance matches the theory's predictions almost perfectly. After Jupiter ignites, that match would fail. The orbit would deviate from Einstein's predictions, not because relativity is wrong, but because the system has changed. A second star introduces new variables, new tugs, and pulls that weren't there before. For scientists, this would be troubling. For Mercury itself, it's irrelevant. The planet is already a hellish, airless rock. A slight shift in orbit changes nothing. Venus, on the other hand, might feel relief. Venus is often called Earth's twin because of its similar size and mass, but the comparison ends there. Venus's atmosphere is 90 times denser than Earth's, composed mostly of carbon dioxide with clouds of sulfuric acid. The greenhouse effect is so extreme that surface temperatures reach 470 degrees Celsius, hot enough to melt lead. Venus is what Earth could become if the greenhouse effect runs away, if the feedback loops spiral out of control. When Jupiter ignites, Venus receives a tiny amount of additional heat, but more importantly, it receives something else, a disruption to its atmospheric circulation. Venus rotates incredibly slowly, taking 243 Earth days to complete one rotation. The atmosphere, however, rotates much faster, circling the planet in just 4 days. This super rotation is driven by complex interactions between solar heating and the planet's slow spin. Adding a second heat source, even a weak one, changes those interactions. Models suggest that Venus's atmospheric winds would slow by about 2% over the course of a century. Not dramatic, but enough to alter the distribution of heat across the planet. Some regions might cool slightly, others might heat even further. Could Venus become habitable? Almost certainly not. The changes are too small, too slow. But they remind us that planets are not static. They respond to their environment, adjusting, adapting, finding new equilibriums. Mars, cold and distant, feels Jupiter's transformation more acutely than Venus. Mars is already on the edge of habitability. Its atmosphere is thin, its surface cold, averaging minus 63 degrees Celsius. Water exists there, frozen in polar ice caps and buried in subsurface reservoirs. But liquid water is rare, appearing only briefly during warm summer days near the equator. When Jupiter ignites, Mars warms. Not by much, only about 0.1 degrees Celsius, but on a planet where temperatures hover near freezing, every fraction of a degree matters. Martian ice begins to sublimate, turning directly from solid to gas. The atmosphere thickens slightly. Dust storms, already a common feature, become more frequent and more intense. The red planet takes on a slightly different hue, a deeper rust, as oxidized iron in the soil reacts with the increasing moisture. Scientists have long speculated about terraforming Mars, transforming it into a world where humans could live without spacesuits. The process would require warming the planet, thickening the atmosphere, releasing trapped carbon dioxide and water. In a twisted irony, Jupiter's ignition accomplishes a tiny fraction of that goal. Mars becomes marginally more hospitable, not through human effort, but through cosmic accident. But any benefit to Mars is overshadowed by the larger problem, orbital instability. Mars's orbit is already more eccentric than Earth's, swinging from about 130 million miles from the Sun at perihelion to 155 million miles at aphelion. This variation drives Martian seasons, creating the dust storms and polar ice cap growth we observe. When Jupiter's gravity shifts, Mars's orbital eccentricity increases, not immediately, not overnight, but steadily over thousands of years. The orbit stretches, becoming more elongated, swinging Mars closer to the Sun at some times and farther away at others. Eventually, perhaps in 10,000 years, perhaps in 50,000, Mars's orbit could cross paths with Earth's. Not physically, not yet. The orbits wouldn't intersect directly, but they would come close enough that gravitational interactions between the two planets could no longer be ignored. Close encounters between planets are rare, but not unheard of. 4 billion years ago, during a period called the Late Heavy Bombardment, the orbits of the giant planets shifted dramatically, sending waves of asteroids and comets crashing into the inner solar system. Earth was hit repeatedly. So was Mars, Mercury, Venus, the Moon. The craters from that bombardment are still visible on the Moon's surface, preserved in airless silence. If Mars and Earth began exchanging gravitational tugs, the late heavy bombardment could repeat. Not as intensely, not as quickly, but over millions of years, the result would be the same chaos. Asteroids would be perturbed from stable orbits. Comets would rain inward. Impact rates would increase. Life on Earth has survived bombardments before. 66 million years ago, an asteroid 6 miles wide struck the Yucatan Peninsula, ending the age of dinosaurs. But life endured. Mammals rose. Evolution continued. Could we survive? Another, perhaps. But the civilization we have built, the cities, the infrastructure, the delicate web of technology that supports 8 billion people, that's more fragile than life itself. A single large impact could collapse nations. Multiple impacts could end civilization. And all of this stems from one changed Jupiter becoming a star. It's worth pausing here to consider scale. The inner solar system is vast. Earth and Mars, at their closest, are about 33 million miles apart. That's 140 times the distance from Earth to the Moon. Space is not empty, but it's sparse. Collisions are unlikely even when orbits shift, but unlikely is not impossible. And over millions of years, unlikely events become probable. Here's a question. If you knew the inner solar system would destabilize over the next 50,000 years, what would you do? Would you try to fix it to nudge orbits back into place with spacecraft and careful planning? Would you prepare to leave to build ships capable of reaching other stars? Or would you simply live, knowing that 50,000 years is longer than all of recorded human history? That whatever happens, it won't touch you or anyone you'll ever know. The truth is, we don't plan for timescales that long. We can barely plan for decades. The problems of distant futures feel abstract, unreal, someone else's burden. But the universe doesn't care about our planning horizons. It moves on its own schedule, patient and indifferent. When Jupiter ignites the inner planets, enter a new era. An era of uncertainty, of slow change accumulating into eventual transformation. The ground beneath our feet remains solid for now. The sky remains blue. But the mechanisms that kept us safe, the gravitational dances that stabilized our orbit, the distances that shielded us from catastrophe, those are eroding. Grain by grain, like sand through an hourglass, the old solar system slips away and something new, something strange takes its place. Yet, even as the inner worlds adjust to their new reality, the outer reaches of the solar system face trials of their own tremors that ripple through gas and ice, reshaping giants that once seemed untouchable. Beyond Mars, beyond the asteroid belt, the solar system changes character. The warmth of the sun fades. Ice becomes as common as rock. Planets grow massive, swollen with hydrogen and helium, wrapped in storms that dwarf entire Earths. This is the realm of the gas giants, Saturn with its impossible rings. Uranus tilted on its side, spinning like a fallen top. Neptune, dark blue and violent, the last major world before the solar system dissolves into the scattered disk and the Oort cloud. These giants have coexisted with Jupiter for billions of years, locked in gravitational relationships so precise they seem choreographed. Saturn orbits the Sun in 29 Earth years. Jupiter takes 12. The ratio is almost exactly 5-2, a resonance that keeps their orbits stable, preventing close encounters that could destabilize either planet. But resonances are fragile. They depend on exact ratios, specific distances, unchanging masses. When Jupiter ignites and becomes a star, the ratios shift, not immediately, not violently, but inevitably. Saturn feels it first because Saturn is closest. At its nearest, Saturn comes within about 4 astronomical units of Jupiter, roughly 370 million miles. In cosmic terms, they're neighbors. When Jupiter's core contracts and its outer layers expand when fusion begins and stellar wind starts flowing, Saturn's orbit responds. The gravitational pull changes subtly but measurably. Saturn's year, which has lasted 29.4 Earth years for eons, begins to lengthen. The change is minuscule at first, a few seconds per orbit, then a few minutes. Over centuries, those minutes accumulate into hours. Over millennia, into days. And as Saturn's orbit stretches the 5-2, resonance with Jupiter breaks. Resonances in orbital mechanics act like springs. They absorb small perturbations, bouncing orbits back into alignment, but push too hard and the spring snaps. The orbits that were stable suddenly aren't. Chaos theory takes over. Chaos doesn't mean random. It means sensitive. Tiny changes in initial conditions lead to vastly different outcomes. A butterfly flaps its wings in Brazil, and a tornado forms in Texas. Saturn shifts its orbit by a fraction of a percent, and Neptune's orbit destabilizes 1,000 years later. Saturn in many ways is Jupiter's twin. Not identical, but similar. Both are gas giants. Both have powerful magnetic fields. Both have extensive moon systems and ring structures. But Saturn is smaller, less massive, and crucially colder. Saturn's average temperature is minus 178 degrees Celsius, even colder than Jupiter. Its internal heat source is weaker, it radiates less energy. And its rings, those stunning bands of ice and rock, are delicate structures held in place by gravitational shepherding from tiny moons. When Jupiter becomes a star, Saturn's rings begin to change. The rings are not solid. They're made of billions of individual particles ranging from dust grains to house-sized boulders, each orbiting Saturn independently. The particles are held in narrow bands by the gravity of small moons called shepherds. Prometheus and Pandora, for instance, orbit on either side of the F-ring, keeping it narrow and defined. But the shepherding process is delicate. It requires precise orbital velocities, exact gravitational tugs. When Saturn's orbit shifts even slightly, the moon's orbits shift too. The balance breaks. Over the course of a few centuries, Saturn's rings begin to spread. The sharp divisions like the Cassini division, a gap you could fit the moon through, start to blur. Particles drift inward or outward depending on their position and velocity. Some fall into Saturn's atmosphere, burning up in streaks of light too faint to see. Others drift outward, escaping into space. Within 10,000 years, Saturn's rings, which have existed for at least 100 million years and possibly much longer, would be unrecognizable. The brilliant sharp bands we see through telescopes would fade into a diffuse haze, beautiful in a different way, but diminished. It's a loss not of life, but of structure, of something ancient and intricate dismantled by forces it can't resist. And yet, Saturn itself endures. The planet is massive enough, stable enough, that losing its rings doesn't threaten its existence. It simply becomes less spectacular, a giant with a fading crown. But what about Saturn's moons? Titan, the only moon in the solar system with a thick atmosphere. Enceladus, with its geysers of water ice shooting into space from a subsurface ocean. Mimas Tethys, Dione Rhea, dozens of smaller bodies, each with its own story. These moons orbit Saturn in carefully balanced arrangements, some in resonance with each other, some shepherding ring particles, some simply drifting in isolation. When Saturn's orbit shifts, their orbits shift too. Titan, the largest, feels the change most acutely. Titan's orbit takes about 16 days, and it's locked in resonance with several smaller moons. As Saturn's gravitational field fluctuates due to the changing relationship with Jupiter, Titan's orbit begins to oscillate. Oscillations in orbit translate to variations in tidal heating. Titan's interior, which might harbor a subsurface ocean beneath its icy crust, experiences periods of increased heating followed by cooling. This cycle could actually benefit any potential life in that ocean, providing periodic injections of energy. But it could also fracture the ice shell, exposing the ocean to space, causing it to freeze and sublimate. Whether Titan's ocean survives depends on details we can't predict, variables too complex to model with certainty. Enceladus, smaller and more fragile, faces a similar dilemma. Its geysers are powered by tidal heating, the friction generated as Saturn's gravity stretches and squeezes the moon. Too much heating, and the geysers become volcanic eruptions, tearing the moon apart. Too little, and the geysers shut down the ocean, freezes, and Enceladus becomes a lifeless ice ball. The balance is precarious, and the 3IATLAS catastrophe tips it. Beyond Saturn lies Uranus, the forgotten giant. Uranus is strange in almost every way. It rotates on its side, tilted 98 degrees from the plane of the solar system. No one knows why. The leading theory suggests a massive collision early in the planet's history knocked it over, and it never righted itself. Uranus's orbit takes 84 Earth years, nearly 3 times longer than Saturn's. It's so distant from the sun that surface temperatures drop to minus 224 degrees Celsius, colder than anywhere else we've measured in the solar system. When Jupiter ignites, Uranus barely notices. The additional heat is negligible at that distance. The gravitational shift is minimal. Uranus continues its slow, tilted rotation, indifferent to the drama unfolding closer to the sun. But indifference doesn't mean immunity. Uranus's orbit, like all orbits, is influenced by the combined gravity of every other object in the solar system. Jupiter is the largest contributor. When Jupiter's mass distribution changes, the cumulative effect takes time to propagate, but eventually it reaches even distant Uranus. Over tens of thousands of years, Uranus's orbit begins to drift outward away from the sun. The change is small, less than 1%, but it's enough to alter the planet's position in the delicate balance of outer solar system dynamics. As Uranus drifts, it starts to interact more strongly with Neptune, the final giant. Neptune is the windiest planet in the solar system, with storms reaching speeds of 1,500 miles per hour. It's also the densest of the gas giants, despite being smaller than Jupiter and Saturn. Neptune's blue color comes from methane in its atmosphere, which absorbs red light and reflects blue. Neptune orbits the Sun once every 165 Earth years, almost twice as long as Uranus. The two planets are currently in a stable configuration, avoiding close encounters, but that stability relies on precise orbital parameters. When Uranus drifts outward, Neptune feels the shift. Its orbit begins to oscillate, swinging slightly inward and outward over each cycle. These oscillations are small, but they compound over time. Within 100,000 years, Neptune's orbit could become chaotic, not in the colloquial sense of random, but in the mathematical sense of unpredictable. Small changes in initial conditions lead to wildly different outcomes. Predicting Neptune's position 1,000,000 years in the future becomes impossible. And if Neptune's orbit destabilizes, it could send ripples through the Kuiper Belt, the region of icy bodies beyond Neptune, where Pluto resides. The Kuiper Belt contains hundreds of thousands of objects, each in a delicate orbit shaped by Neptune's gravity. If Neptune shifts, the Kuiper Belt could scatter. Icy bodies would be flung inward toward the inner solar system. Some would become comets, blazing trails across the sky as they approach the sun. Others would collide with planets, moons, or each other. This isn't speculation. We've seen it happen before. 4 billion years ago, during the late heavy bombardment, a shift in the outer planet's orbit sent a wave of comets and asteroids crashing into the inner solar system. The moon's surface is scarred with craters from that event. So is Mercury. So is Mars. If Neptune destabilizes, the late heavy bombardment could happen again. Not as intensely, not as quickly, but over millions of years, the effect would be similar. Increased impacts, disrupted orbits, chaos, spreading from the outer reaches inward. Here's a thought that should unsettle you. The outer solar system is not empty space. It's filled with ice and rock leftovers from the solar system's formation, scattered through a volume larger than we can easily comprehend. Most of these objects are small, harmless, too distant to threaten anyone. But distance is not safety. Distance is just delay. When orbits shift, when gravitational balances break, those distant objects become weapons flung inward by forces they don't understand, aimed at targets they can't see. We like to think of the solar system as stable as safe. We look up at Saturn's rings and Neptune's storms and see beauty, permanence, a cosmic order that's been here longer than we have and will outlast us. But stability is not permanence. It's just slow change. And sometimes change accelerates. The outer giants in many ways are more vulnerable than the inner planets. They're held together by gravity and rotation, massive but diffuse, sensitive to perturbations we can barely measure. They don't have solid surfaces to anchor them. They're clouds wrapped around cores we've never seen. If Jupiter becomes a star, those clouds will shift. Those cores will feel new pressures. And the giants, which have been silent witnesses to the inner solar system's dramas for billions of years, will finally speak. Not with words, not with intention, but with motion, with change, with the slow, inexorable reconfiguration of orbits that have been stable since before Earth had oceans. It's humbling in a way, to realize that the cosmos doesn't care about our categories, our labels, our assumptions of permanence. Saturn's rings will fade, Neptune's orbit will wobble, Uranus will drift. And all because one planet 5 astronomical units away crossed a line it was never supposed to cross. But even these massive transformations pale beside what happens to the smaller worlds, caught directly in Jupiter's new light, the moons that have no choice but to endure the fire. There are places in the solar system where life might exist beyond Earth. Not intelligent life, not civilizations, but something simpler. Microbes, perhaps. Organisms clinging to existence in the dark beneath ice and water that hasn't seen sunlight in billions of years. One of those places is Europa, the 4th largest moon of Jupiter, a world wrapped in ice so smooth it reflects light like a mirror. Beneath that ice, locked away from view, scientists believe there's an ocean, not a small one, not a puddle, an ocean twice the volume of all of Earth's oceans combined. And if there's water, if there's heat, if there's chemistry, then maybe there's life. But when Jupiter ignites Europa's chances of harboring life, don't improve. They collapse. Let's talk about what makes Europa special, because understanding what it is helps us grasp what it loses. Europa is slightly smaller than Earth's moon, about 1,900 miles in diameter. Its surface is ice water. Ice frozen to a hardness that rivals steel. But the ice is young, geologically speaking. There are almost no impact craters, which means the surface renews itself somehow. That renewal comes from below. The ocean beneath the ice is kept liquid by tidal heating, the same force that creates friction in Io's interior and drives its volcanoes. As Europa orbits Jupiter, it's squeezed and stretched by Jupiter's immense gravity. This flexing generates heat enough to melt ice and sustain an ocean that would otherwise freeze solid. The ice shell is estimated to be about 10 to 15 miles thick. Beneath it, the ocean could be 60 miles deep or more. And at the bottom of that ocean on the rocky seafloor, there might be hydrothermal vents, hot springs, where mineral-rich water seeps up from the moon's interior. On Earth, hydrothermal vents are oases of life. Tube worms, clams, bacteria, entire ecosystems thrive in the pitch dark, feeding on chemical energy rather than sunlight. If Europa has similar vents, it could have similar life. But Europa's delicate balance depends on tidal heating, staying within a narrow range. Too little and the ocean freezes. Too much and the ice shell cracks, the ocean boils and everything dies. When Jupiter becomes a star, the tidal forces don't just increase, they destabilize. Here's how tidal heating works. As Europa orbits Jupiter, it experiences varying gravitational pull depending on its distance. At the closest point, Jupiter's gravity pulls harder. At the farthest point, the pull is weaker. This variation creates a tidal bulge, a slight deformation of Europa's shape. If Europa's orbit were perfectly circular, the tidal bulge would stay in the same place, and there would be no friction, no heating. But Europa's orbit is slightly elliptical, eccentric, which means the bulge shifts position as the moon orbits. The shifting creates internal friction, and friction generates heat. The eccentricity of Europa's orbit is maintained by gravitational interactions with the other Galilean moons, Io, Ganymede, and Callisto. They're locked in what's called a Laplace resonance, a gravitational dance, where for every orbit Europa makes, Ganymede makes half an orbit and Io makes two. This resonance prevents the orbits from becoming circular, ensuring that tidal heating continues indefinitely. It's a beautiful system, precise and self-sustaining, and it's been stable for billions of years. But when Jupiter's mass distribution changes, when the core contracts and the outer layers expand, the resonance breaks. It doesn't happen immediately. Orbital resonances are robust, resistant to small perturbations. But Jupiter's transformation is not a small perturbation. It's a fundamental change in the gravitational landscape. Over the course of a few decades, Europa's orbit begins to shift. The eccentricity increases subtly at first, then more dramatically. The tidal bulge grows larger. The internal friction intensifies. Europa's ice shell begins to crack. Not gently, not slowly. The cracks spread like lightning fractures, racing across the surface at hundreds of miles per hour. Sections of ice the size of continents tilt, break apart, shift. Some sink into the ocean below. Others rise, pushed upward by pressure from beneath. Water from the ocean seeps into the cracks, rising toward the surface. In the near vacuum of space, it boils instantly, turning to vapor, freezing into ice crystals that fall back down like snow. Europa's thin atmosphere, normally composed of just traces of oxygen, thickens with water vapor. From a distance, Europa begins to look hazy, veiled, as if it's exhaling after holding its breath for eons. But this is not a gentle awakening. It's a death spiral. As the ice shell fractures, the ocean is exposed to space. Water doesn't remain liquid in vacuum. It either freezes or evaporates, depending on temperature and pressure. Near the cracks where the ocean meets vacuum, water boils away, escaping into space, lost forever. The ocean begins to shrink, not overnight, but steadily year after year. In a few thousand years, Europa's vast subsurface ocean, which might have harbored life for billions of years, could be reduced to scattered pockets of ice and brine, too small, too cold, too fragmented to sustain anything complex. If there was life in Europa's ocean, it dies. Not from violence, not from impact or explosion, but from suffocation, from the slow removal of the one thing it needed to survive: liquid water. It's a quiet extinction witnessed by no one, mourned by nothing. Ganymede, the largest moon in the solar system, faces a different kind of catastrophe. Ganymede is bigger than Mercury, the only moon with its own magnetic field generated by a liquid iron core deep inside. That magnetic field creates a magnetosphere, a protective bubble that shields the surface from Jupiter's intense radiation. Ganymede also has an ocean buried beneath layers of ice and rock, perhaps 100 miles deep. But unlike Europa, Ganymede's ocean is separated from the surface by so much material that it's unlikely to harbor life. The conditions are too isolated, too cold, too cut off from energy sources. When Jupiter ignites, Ganymede's magnetic field becomes a liability. A star doesn't just emit light and heat. It emits charged particles, a stellar wind streams of electrons and protons flowing outward at hundreds of miles per second. Our sun does this constantly. Earth's magnetic field deflects most of it, channeling the particles toward the poles where they create auroras. But Jupiter's stellar wind is different. It's not as strong as the Sun's, but it's close. Ganymede, orbiting less than 700,000 miles from Jupiter, sits directly in the path of this wind. Ganymede's magnetic field tries to deflect the incoming particles just as it always has. But the density of the stellar wind is far greater than the radiation Jupiter emitted as a planet. The magnetosphere compresses, shrinking under the pressure. Within weeks, the magnetosphere fails. It doesn't disappear. The magnetic field is still there, but it can no longer hold back the onslaught of particles. The stellar wind reaches the surface. Ganymede's icy crust, which has been relatively stable for billions of years, begins to erode. Charged particles strike water ice molecules, breaking them apart, releasing hydrogen and oxygen into space. The surface darkens, scarred by radiation. Damage peppered with tiny craters where particles have blasted away material at the molecular level. Over centuries, Ganymede loses mass. Not dramatically, not enough to change its orbit significantly, but enough to alter its appearance. The bright reflective ice that once covered much of the surface turns dark reddish-brown, coated with radiation-damaged material called tholin, the same substance that colors Pluto's surface. Ganymede becomes a ghost of what it was, a world marked by invisible violence. Io, the most volcanically active body in the solar system, doesn't need much help to become hellish. It's already there. Hundreds of active volcanoes dot its surface, erupting plumes of sulfur and sulfur dioxide that rise 200 miles into space before falling back down. Io's volcanism is powered entirely by tidal heating, the same process that warms Europa's ocean. But Io is closer to Jupiter, and the tidal forces are stronger. The moon is literally being pulled apart and squeezed back together with every orbit. When Jupiter becomes a star, those tidal forces increase. Io's orbit decays slightly, bringing it closer to the new star. The tidal heating intensifies. Volcanic eruptions become more frequent, more powerful. Lava flows merge into seas molten sulfur, covering vast regions. The surface temperature, already scorching in places, rises even higher. Io begins to glow, not just from reflected light, but from its own heat, a dull red ember orbiting a pale yellow star. Eventually, Io's crust can't hold. Sections collapse into the magma below. The moon becomes less solid, more molten, a ball of lava barely held together by gravity. In a few tens of thousands of years, Io might disintegrate, entirely torn apart by the very forces that made it unique, scattering debris in a ring around Jupiter. And Callisto, the most distant of the Galilean moons, watches from afar. Callisto is ancient, heavily cratered quiet. It doesn't have the volcanism of Io, the fractured ice of Europa, or the magnetic field of Ganymede. It's just a ball of ice and rock, cold and inert, unchanged for eons. When Jupiter ignites, Callisto remains mostly unaffected. The tidal forces are weak at its distance. The stellar wind is diffuse. The additional heat is negligible. But Callisto's orbit does shift. Slowly, over thousands of years, it drifts outward, pushed by the pressure of Jupiter's stellar wind, nudged by gravitational interactions with the other moons as their orbits change. Eventually, Callisto might escape Jupiter's gravity, entirely becoming a rogue moon, a wanderer adrift in the outer solar system, carrying with it the frozen record of a time when Jupiter was a planet and the moons danced in harmony. The loss of the Galilean moons is not just a loss of objects, it's a loss of potential. Europa might have harbored life. Ganymede might have taught us about magnetic fields and planetary interiors. Io showed us that tidal heating can power volcanism on a scale we've never seen elsewhere. These moons were laboratories, natural experiments running for billions of years, teaching us about processes we could never recreate on Earth. And in the 3IATLAS scenario, they're destroyed, not by intention, not by malice, but by proximity. They're simply too close to a transformation they can't survive. It raises a question: how much do we lose when we lose places we've never visited? Europa's ocean might be empty, sterile, devoid of life. Or it might be teeming with organisms we've never imagined. We don't know because we haven't looked. And if the 3IATLAS catastrophe happened, we'd never get the chance. There's a mission planned, the Europa Clipper set to launch in the late 2020s, designed to orbit Jupiter and make repeated flybys of Europa, mapping the ice shell, measuring the ocean's depth, searching for plumes of water vapor that might carry samples of the subsurface ocean into space. If that mission succeeds, if it finds evidence of life, it would be one of the most profound discoveries in human history. Proof that life arose independently somewhere other than Earth, that we're not alone, even if our companions are just microbes in a dark ocean. But if Jupiter ignited before that mission launched, before we had a chance to look, we'd lose not just the discovery, but the possibility of discovery. And possibility in many ways is more valuable than certainty. The tragedy of the Galilean moons is that they're caught in forces beyond their control, shaped by a parent planet that's now become something else, something incompatible with their existence. They can't escape, they can't adapt, they can only endure until endurance is no longer possible. In that sense, they mirror every fragile system in the universe, every delicate balance that depends on conditions staying the same. We think of stability as the default, as natural, but stability is rare. It's the exception, not the rule. And when it breaks, when the conditions shift, when the gentle giant becomes a burning star, those who depended on gentleness are left with nothing but fire. Yet fire does not burn in isolation. And as the moons crumble, the disturbance spreads further, still rippling through belts of rock and fields of ice, unsettling the forgotten edges, where silence once reigned absolute. Between Mars and Jupiter lies a wasteland of stone and metal, millions of fragments orbiting the sun in a band we call the asteroid belt. Most people imagine it as a dense field of rocks, like a minefield in space, but the reality is far emptier. You could fly through the asteroid belt and likely never see a single rock with your naked eye. The distances are vast, the objects scattered. Yet this emptiness has structure. The asteroids orbit in families clustered by composition and origin. Some are rocky remnants of a planet that never formed. Others are metallic fragments of ancient cores that shattered long ago. And a few are icy wayward comets that wandered too close to the sun and stayed. These objects have orbited peacefully for billions of years, held in place by a gravitational balance between the sun and Jupiter. But when Jupiter becomes a star, that balance shatters and the asteroid belt begins to dissolve. The process starts subtly. Jupiter's transformation changes its gravitational influence not in total strength, but in how that strength is distributed across space. Asteroids in certain orbits, particularly those in what are called resonances with Jupiter, begin to feel a difference. A resonance is a special orbital relationship, where an asteroid completes a certain number of orbits in the same time Jupiter completes a different number. For example, the 3-to-1 resonance means an asteroid orbits the Sun 3 times for every one Jupiter orbit. These resonances create gaps in the asteroid belt regions where almost no asteroids exist, because any object that wanders into those orbits gets kicked out by repeated gravitational nudges from Jupiter. When Jupiter ignites, those nudges change. They become stronger in some places, weaker in others. Asteroids that were stable for eons suddenly aren't. Their orbits shift sometimes inward toward the sun, sometimes outward toward the outer solar system. Within 1,000 years, the structure of the asteroid belt begins to blur. Gaps that were clean and sharp become fuzzy. Families of asteroids that shared similar orbits scatter. Some objects collide, fragmenting into smaller pieces. Others are ejected entirely, flung out of the belt into trajectories that cross the orbits of planets. And some of those trajectories cross Earth's orbit. Earth has been hit by asteroids before. 66 million years ago, an asteroid roughly 6 miles wide struck the Yucatan Peninsula, creating the Chicxulub crater and ending the reign of the dinosaurs. The impact released energy equivalent to billions of nuclear bombs, triggering wildfires, tsunamis, and a global winter that lasted for years. That asteroid came from the main belt, perturbed into an Earth-crossing orbit by gravitational interactions we still don't fully understand. It took millions of years to drift inward, and when it finally hit, it was traveling at about 45,000 miles per hour. In the 3IATLAS scenario, the number of asteroids perturbed into Earth-crossing orbits increases dramatically. Not immediately, not in our lifetimes, but over tens of thousands of years, the impact rate would rise. How much computer models suggest the rate could increase by a factor of 10 or more. Instead of a civilization-ending impact every 100 million years, we might face one every 10 million years. Instead of smaller impacts happening every few 100,000 years, they might happen every few tens of thousands of years. These timescales feel distant, abstract, not something to worry about now. But civilizations, if they survive long enough, do have to worry. A species that lasts for millions of years will face these events not as remote possibilities, but as certainties. And if we knew the asteroid belt was destabilizing, if we could see the trajectories shifting, would we do anything? Could we? Deflecting an asteroid is theoretically possible. NASA has tested it with the DART mission Double Asteroid Redirection Test, which successfully altered the orbit of a small asteroid by crashing a spacecraft into it. The impact changed the asteroid's velocity by a fraction of a percent, but that was enough to shift its orbit measurably. For a large asteroid, one that could end civilization deflection would require years of warning and immense resources. You'd need to detect the asteroid decades before impact, calculate its trajectory precisely, and launch multiple missions to nudge it off course gradually. If the asteroid belt destabilizes and sends hundreds of new objects into Earth-crossing orbits, tracking all of them becomes a monumental task. We'd need a vastly expanded observation network, constant vigilance, and the ability to respond to multiple threats simultaneously. It's doable, but it requires planning investment and a willingness to take the threat seriously even when it feels distant. History suggests we're not great at that. Beyond the asteroid belt lies another reservoir of ancient debris, far larger and far more dangerous, the Kuiper Belt and the Oort cloud. These regions contain billions of icy bodies, comets, waiting to be disturbed. The Kuiper Belt sits just beyond Neptune, a disk of frozen objects ranging from tiny ice chunks to dwarf planets like Pluto. It's the source of short-period comets objects that orbit the sun in less than 200 years. When something perturbs a Kuiper Belt object, sending it inward, it becomes a comet trailing a tail of gas and dust as the sun's heat vaporizes its icy surface. The Oort cloud is even more distant, a spherical shell surrounding the entire solar system, extending halfway to the nearest star. It's the source of long-period comets objects that take thousands or even millions of years to complete a single orbit. We've never seen the Oort cloud directly. It's too far, too faint. But we know it's there because comets keep arriving from its direction. When Jupiter becomes a star, its gravitational influence extends outward, rippling through the Kuiper Belt, and eventually reaching the inner edges of the Oort cloud. Objects in these regions, which have been in stable orbits for billions of years, begin to shift. The effect is gradual, almost imperceptible at first, but over millennia, the cumulative changes add up. Objects that were safely distant drift inward. Orbits that were stable become chaotic. The result is an increase in cometary activity. More comets fall toward the inner solar system. More bright tails appear in Earth's night sky. For a few generations, it might seem beautiful, a renaissance of celestial wonders, new comets appearing every few years. But comets are not just beautiful, they're dangerous. In 1994, we watched Comet Shoemaker-Levy 9 break apart and slam into Jupiter. Each fragment released energy equivalent to millions of nuclear bombs, leaving scars in Jupiter's atmosphere the size of Earth. Jupiter absorbed the impact without consequence its immense gravity and thick atmosphere shielding it from harm. Earth has no such shield. If a comet the size of Shoemaker-Levy 9 hit Earth, it would be an extinction event, potentially worse than the asteroid that killed the dinosaurs, because comets travel faster, carrying more kinetic energy. The likelihood of a direct hit is still low, even with increased cometary activity. Space is vast and Earth is small, but low is not zero, and over millions of years the improbable becomes inevitable. There's another consequence to consider, one that's less dramatic but equally profound: the reshaping of the habitable zone. The habitable zone is the region around a star where liquid water can exist on a planet's surface, where temperatures are neither too hot nor too cold for life, as we know it. For our Sun, the habitable zone stretches from about 0.95 astronomical units just inside Earth's orbit to about 1.37 astronomical units roughly halfway between Earth and Mars. Earth sits comfortably in the middle. Mars is on the outer edge, too cold for liquid water, except in rare, brief instances. When Jupiter becomes a star, it creates a second habitable zone centered on itself. This zone would be much closer to Jupiter than our Sun's habitable zone is to the Sun, because Jupiter, even as a star, is far dimmer. Rough calculations suggest Jupiter's habitable zone would extend from about 0.02 to 0.1 astronomical units, or roughly 1 to 5 million miles from the new star. That's closer than Io's current orbit. In other words, there's no existing moon or planet in Jupiter's new habitable zone. The Galilean moons are too cold, even with the additional heat. And the inner solar system is in the Sun's habitable zone, not Jupiter's. So, the 3IATLAS catastrophe doesn't create new opportunities for life to thrive. It simply disrupts the one habitable zone we have, shifting Earth's climate, destabilizing its orbit, and threatening it with increased impacts. But let's imagine for a moment that humanity survives, that we detect the destabilization, early build deflection systems, adapt our civilization to a warming climate and shifting seasons. Let's imagine we endure the first 1,000 years, the first 10,000, the first million. What then? If we survive long enough, we'd face a choice. Do we stay in the solar system, accepting the risks, trusting our technology to protect us? Or do we leave, venturing to other stars, where the gravitational landscape is more stable? Interstellar travel is not easy. The nearest star, Proxima Centauri, is 4.2 light-years away. With current technology, a journey there would take tens of thousands of years. Even with advanced propulsion systems, fusion drives, or light sails, the trip would still take decades or centuries. But if the alternative is staying in a solar system that's slowly falling apart, the calculation changes. Leaving becomes not an adventure, but a necessity. We've never built a generation ship, a spacecraft designed to support human life for centuries, while traveling between stars. We've never had to. But the engineering is theoretically sound. You'd need a closed-loop ecosystem, artificial gravity radiation, shielding, and a population large enough to maintain genetic diversity. It's doable. Difficult, expensive, requiring resources and planning on a scale we've never attempted, but doable. And if the 3IATLAS catastrophe gave us enough warning, if we saw it coming centuries or millennia in advance, we'd have time to prepare. The irony is that Jupiter's transformation, the very event that threatens us, might also be the catalyst that pushes us to become an interstellar species. Sometimes survival requires leaving home. But there's a deeper question here, one that goes beyond engineering and survival. What do we owe to the solar system that created us? Do we have a responsibility to preserve it, to protect the moons and planets and asteroid fields that have existed for billions of years? Even if they're not alive, even if they'll never know we cared? Or is our only responsibility to ourselves, to our species, to the continuation of human consciousness and culture, wherever that takes us? There's no right answer. But the question is worth asking. Because the 3IATLAS catastrophe, unlikely as it is, forces us to confront the reality that the universe doesn't owe us stability. The solar system we were born into is not guaranteed to last forever. Change is inevitable. Chaos is always one perturbation away. And when that chaos comes, whether it's Jupiter igniting or some other cosmic event we haven't imagined yet, we'll have to decide, do we adapt? Or do we leave? Do we fight to preserve what we have? Or do we accept loss and move forward? The asteroid belt will dissolve. Comets will rain inward. The habitable zone will shift. These are the consequences of a second star, the ripples spreading outward from a transformation we never asked for and can't undo. But consequences are not conclusions. They're just the next chapter, the continuation of a story that began 4.5 billion years ago and will continue long after we're gone. Unless we choose to write a different ending, one where we don't just survive the chaos, but transcend it, carrying the light of consciousness beyond the reach of any star, any catastrophe, any fire that burns where it shouldn't. And as these choices loom before us, one final truth remains to be reckoned with, a truth that returns us to the present, to the quiet sky, to the sleeping giant that has not yet stirred. We've walked through fire tonight. Not real fire, not yet, but the kind that exists in equations and simulations, in the careful mathematics of what could happen if one giant decided to wake up and burn. We've watched Jupiter transform from protector to threat, seen its moons crumble, its neighbors wobble, the entire solar system reshaped by a change that should never occur. We've traced the physics from ignition to catastrophe, following the chain of consequences as they ripple outward, touching everything, sparing nothing. But here's what we haven't done. We haven't stepped outside and looked up at the real Jupiter, the one that exists right now, the one that's been peaceful for 4.5 billion years and shows no sign of changing. Because Jupiter is not going to ignite. The universe doesn't have a mechanism for it. The mass isn't there. The conditions don't exist. The 3IATLAS scenario is a thought experiment, a way of understanding how fragile our solar system is, how much we depend on things staying the same, and things have stayed the same for a very long time. Let's return to reality for a moment, because reality, as it turns out, is just as fascinating as catastrophe. Jupiter is out there right now, glowing faintly in reflected sunlight, spinning once every 10 hours, shepherding its moons through their ancient dance. It's been doing this since before Earth had continents, before life crawled onto land, before humans looked up and wondered what those wandering stars might be. Galileo Galilei, in 1610, pointed a crude telescope at Jupiter and saw 4 moons circling it. He didn't know what they were at first. He thought they might be stars lined up by coincidence. But night after night, he watched them move orbiting the giant, and he realized something profound. Not everything in the cosmos revolves around Earth. That observation, simple as it seems, now helped dismantle centuries of dogma. It was one of the first pieces of evidence that the universe is larger, stranger, more indifferent to human assumptions than anyone had dared imagine. Jupiter has been teaching us ever since. In 1973, Pioneer 10 became the first spacecraft to visit Jupiter flying past, at a distance of about 81,000 miles. It sent back grainy images of the Great Red Spot measurements of the magnetic field data on the radiation belts. The mission lasted only a few hours, but it opened a door. Voyager 1 and 2 followed in 1979, capturing stunning images of the Galilean moons, discovering volcanic eruptions on Io, seeing Europa's fractured ice for the first time. Those images are still breathtaking decades later, reminders that beauty exists in places we've never touched. The Galileo spacecraft, launched in 1989, spent 8 years orbiting Jupiter, studying the planet and its moons in unprecedented detail. It dropped a probe into Jupiter's atmosphere, measuring temperature, pressure, and composition as it descended, transmitting data until the crushing pressure destroyed it. And most recently, Juno, which arrived at Jupiter in 2016, has been mapping the planet's gravity field, peering beneath the cloud tops, revealing that Jupiter's core is larger and more diffuse than we thought, that the interior is far more complex than our models predicted. Every mission teaches us that we know less than we assumed. Every new image raises new questions. Jupiter is not a solved problem. It's an ongoing mystery, layered and deep, resistant to easy answers. And that's comforting in a way, because it means there's still more to learn, more to discover, more reasons to keep looking up. The 3IATLAS scenario asks us to imagine a universe where Jupiter becomes something it's not. But the real universe is already strange enough. There are exoplanets out there, planets orbiting other stars that are hot. Jupiter's gas giants that orbit closer to their stars than Mercury orbits the Sun. These planets shouldn't exist. According to our models of planetary formation, gas giants should form far from their stars, where it's cold enough for ice to condense. But they do exist. We've found hundreds of them, which means our models were incomplete, our understanding limited. The universe is teaching us patiently that what we think is impossible might just be something we haven't figured out yet. There are also brown dwarfs, those in-between objects that are almost stars, but not quite. Some of them have storms, magnetic fields, even planets orbiting them. They blur the line between planet and star, challenging our neat categories, reminding us that nature doesn't care about our definitions. And there are binary star systems, two stars orbiting each other, sometimes with planets caught in the gravitational dance between them. Life on a planet in a binary system would experience sunrises and sunsets unlike anything we know. Some days would have two suns in the sky. Some nights would have none. We live in a universe of variety of configurations we're only beginning to catalog. The 3IATLAS scenario, implausible as it is, helps us understand the mechanics of that variety. The rules that govern how stars and planets interact, the consequences of crossing thresholds we thought were fixed. It's not about fear, it's about knowledge, about mapping the boundaries of what's possible so we know where we stand. And where we stand is in a solar system that's been remarkably stable, remarkably kind for billions of years. The sun burns steadily. The planets orbit predictably. The asteroid belt stays mostly in place. We've had time to evolve, to build civilizations, to develop technology, to look outward and ask questions. That's not guaranteed. There are solar systems out there that are chaotic, unstable, where planets collide or get ejected into interstellar space. There are stars that flare unpredictably, sterilizing any planets that might have harbored life. There are regions of the galaxy where supernovas explode every few million years, bathing entire star systems in lethal radiation. We got lucky, not because the universe favors us, but because out of billions of stars, billions of planets, some are bound to be in stable configurations, just by chance. And we happen to be in one of those. But luck doesn't last forever. On cosmic timescales, everything changes. The sun will eventually exhaust its hydrogen swell into a red giant and consume Mercury, Venus, and possibly Earth. That's guaranteed. It's written in the physics of stellar evolution. But it won't happen for another 5 billion years. And 5 billion years is long enough that worrying about it now seems absurd. The 3IATLAS catastrophe is different. It's not something we can predict with certainty. It's not on a timeline we can calculate. It's a low probability, high impact event, the kind of thing that keeps scientists up at night, not because it's likely, but because it's possible. Should we worry about it? Probably not. There are more immediate threats. Climate change, asteroid impacts, pandemics, nuclear war. These are dangers we can measure, predict, and potentially mitigate. But should we think about it? Absolutely. Because thinking about low probability catastrophes helps us build resilience. It helps us develop technologies, strategies, and mindsets that prepare us for the unexpected. If we ever develop the ability to deflect asteroids, we'll be able to deflect comets too. If we learn to live in space, we'll be able to survive disruptions to Earth's climate. If we build interstellar spacecraft, we'll have a backup plan if the solar system becomes inhospitable. These capabilities don't come from fear. They come from curiosity, from the desire to explore, to understand, to push boundaries. The 3IATLAS scenario is just another boundary, one more edge of the map, where we can test our knowledge and see how far it reaches. And here's the beautiful part. We don't have to face these challenges alone. Humanity is a collective effort. Every scientist who studies Jupiter, every engineer who designs spacecraft, every person who looks up at the night sky and wonders contributes to our understanding of the cosmos. We're building a legacy of knowledge piece by piece, generation by generation. And that knowledge will outlast us. It will be there for our children, for their children, for civilizations. We can't imagine helping them navigate a universe that's vast and strange and indifferent, but also full of wonder. Jupiter will keep spinning. Its moons will keep orbiting. The solar system will keep turning patient and reliable, at least for now. And we'll keep watching, measuring, learning, asking questions that don't have easy answers. Because that's what we do. We're curious creatures, restless and relentless, never quite satisfied with what we know. We look at a peaceful giant in the sky and ask, what if it weren't peaceful? What if it changed? What would happen to us? And in asking those questions, we discover not just facts about the universe, but truths about ourselves, about our resilience, our creativity, our ability to imagine catastrophes and then figure out how to survive them. The fire we imagine tonight will never burn. Jupiter will remain a planet cold and distant, protecting us from dangers we'll never see. The 3IATLAS catastrophe will stay in the realm of thought experiments, simulation, what-ifs. But the lessons remain. The reminder that stability is temporary, that the universe doesn't owe us safety, that the ground beneath our feet, the sky above our heads, the rhythms we depend on, all of it, could change given the right conditions. And if it does change, we'll adapt, because we always have. Through ice ages and asteroid impacts, volcanic eruptions and mass extinctions, life has endured. Humanity has endured. And whatever comes next, whatever fires might burn in distant futures, we'll find a way through. Not because we're special, not because we're chosen, but because we're here. And being here means trying, learning, surviving one question at a time. So, tonight when you step outside, look for Jupiter. It's there, a pale dot in the darkness, steady and bright. It won't burn. It won't change. It will just be as it always has been, a quiet guardian in the night. And maybe that's enough. Maybe knowing that some things stay the same, even as we imagine all the ways they could fall apart, is a kind of peace. You've drifted with me through impossible fires, through crumbling moons and destabilized orbits, through the mathematics of catastrophe and the poetry of survival. Thank you for listening. Thank you for wondering. Thank you for staying curious even when the questions lead to uncomfortable places. The universe is vast, and we've only just begun to explore it. There are more stories waiting, more mysteries hidden in the dark, more questions that need asking. Rest now. Dream gently. And when you're ready, we'll wander again into the quiet places where science meets wonder, where knowledge softens into sleep. Until then, look up. The stars are still there. The giants are still sleeping. And the night, as always, is full of light. Good night.